Hello students. In the lecture video 8, so that is in this class I am going to solve numerical problems on dynamic consideration, that is to find the eigenvalues and eigenvector for the step bar system. Okay, so after deriving the three equations under dynamic consideration, with the help of those equations, okay, so we are going to calculate the eigenvalues and eigenvector for the step bar problem. Okay, so this problem, if they ask in the examination, means around directly they may ask you around 16 mark. Okay, so this is very important problem for the step bar problem. Okay, so look at this. So here I am going to covering the evaluation, that is a calculation of the eigenvalues and eigenvector for the step bar problem. Okay, so this is the covering. I am today class I am going to solve this problem. Okay, if you perfect this problem, means the bar is very simple problem. Okay, so this will come under this only. Okay, this is a single bar, this is a two bar element. Okay, so look at. Okay, so now I am going to calculate the how to calculate the eigenvalues and eigenvector for the stepped bar equation. Okay, so before solving this, we have to understand the equations first. Okay, so here so many formulas will come that we have to by heart, or you have to remember those formula. Okay, so without formula you cannot solve this type of the numerical problems in under FEM. Okay, so now, so question that is the first problem. So look at carefully. So problem number 1. Okay, so determine the eigenvalues and the eigenvector for the stepped bar. Okay, so for the shown in below figure, so take the Young modulus for the given stepped bar, that is material property is given what 200 gigapascal, and this symbol called as a rho, so that is the mass density for the given stepped bar is equal to 7830 kg per meter cube. Okay, so this is the question. So our aim is to find the eigenvalues and eigenvector. Okay, so they are given what stepped bar. Okay, stepped bar nothing but what, so the cross section area going to changes. Okay, for the first element is different, second element is different, that is called as step bar system. Okay, so here they given along with, they are telling that consider the Young modulus or the mass density is equal to 200 gigapascal and 7830 kg per meter cube. Okay, so to calculate the eigenvalues and eigenvector. Okay, so we have the formula for to calculate the eigenvalues and eigenvector. Use those formula, you can get the answer. Okay, this is very simple. So first, so this is a question they given. So this is a step bar. So this area is different, this area is different. Okay, so here two elements are there. So element number 1, element number 2. So how many nodes are there? So node number 1, 2, 3 is there. Okay, so length of the first element is given 0.5, and the length of second element is given also same, that is L1 L2 is equal to 0.5. Okay, so area for this one is 100 and second element area is 50. Okay, so note on the given data first. Okay, so here note on the given data is equal to Young modulus 200 gigapascal, mass density is equal to 7830 kg per meter square meter cube. So area and area 1, area 2, length L1 L2. Okay, so this is a given data. Note on the first step. Okay, so first step you have to consider, you have to assume here the two elements are there, three nodes are there. Okay, so that you have to keep it in mind. Okay, now we have the formula, that is eigenvalues and the eigenvector is equal to capital K minus 2m, that is into x is equal to 0. Okay, so here k, that is if you wrote this matrices. Okay, so that is k minus lambda m is equal to 0. Okay, so here we need to calculate the values of this k value and m value. Okay, so substitute, you are going to get the eigenvalues and eigen vector for the given answer. Okay, so we know that this is the first step. So we know that the element stiffness matrix for the first elements. Okay, so ae by l is equal to, this is the stiffness matrix formula is there. Substitute. Now our aim is to calculate this k value. Okay, then m value, substitute in this, so you are going to get. Okay, K1 is equal to, so we have the formula, that is stiffness matrix K1 is equal to A1 E by L 1 minus 1 minus 1 1. Okay, so substitute the area, we have Young modulus, we have a length value, we have substitute in this equation, so you are going to get this equation. Okay, so that is, if you simplify this, so you outside inside we are going to get 10 to the power of 7. If you multiply inside means 4 minus 4 minus 4 4. Okay, so K1 is equal to 10 to the power of 7, 4 minus 4 minus 4 1. Okay, so for the first element, node between 192, so 192 you have to write here. Okay, this is the first element. So similarly calculate the second element. Okay, so second element area going to changes, so substitute area here different. Okay, substitute a e by l. Okay, so 1 minus 1 minus 1 1. So k2 is equal to 10 to the power of 7, 2 minus 2 minus 2 2. Okay, so since k2 is belongs to the node number 2 and 3, so node on here 2 3, so 2 3. Okay, so the global stiffness matrix is equal to what? So already this is, we are, I think you are perfect now how to add this. Okay, so since maximum nodes are 3 is there, so both the said the 10 to the power of 7 is common is there, k is equal to 10 to the power of 7. So it is 3 into 3 matrix. So note down here 4 minus 4 0 minus 4 6 minus 2 0 minus 2 1. Okay, how to add this I already told you. Note down first 3 into 3 matrix. So look at this 1 1 in the both the matrix, you have to check, this is the second element, this is the first element. Okay, so 1 1 is 4 is there, here 1 1 not there, so put here 4. Okay, like that you have to add, calculate the global stiffness matrix. Okay, So this is global stiffness matrix. So once if you calculate the global stiffness matrix, in the formula we have the again mass matrices, that is elemental mass matrix is there. So now you calculated this value, now you calculate this m value. Okay, so how to calculate this m value? So elemental mass matrix, we have the formula is equal to, already we derived this equation in the derivation. Okay, so elemental mass matrix is equal to density, mass density area length by 6 2 1 1 2. Okay, so here you have to calculate the elemental mass matrix for first element and the second element. Okay, so substitute the mass density is common, so a1 and length of the first element divided by 6 this. Okay, so if you calculate this, okay, so you are going to get m1 is equal to 0.1305. okay, so if you solve this, so you are going to get this equation. Okay, so this is related to mass node between 1 to 1 2. Okay, similarly calculate the elemental mass matrix for the second element. Okay, just to replace here a 100 to mm, so second area you have to substitute here 15 to 10 to the power of minus 6. Okay, if you simplify this, so you are going to get this. Okay, so elemental mass matrix is equal to 0.653. okay, so this equation. Okay, with the help of this equation, mass 1 and mass 2, calculate the global elemental mass matrices again. Okay, 1 2 3 1 2 3, again you have to add. So here 1 1 0.13 is there, here not there, so 0, so 0.13 plus 0 is equal to 0.13. okay, like that you have to calculate this elemental mass matrices. Okay, so now we calculated the global stiffness matrix and mass elemental mass matrices. So substitute this equation and that global stiffness matrix in equation number 1. okay, that is k minus lambda by m is equal to 0. okay, so k value substitute here, elemental mass matrices you have to minus lambda, you have to substitute here. Okay, so since the node 1s are fixed is there, okay, in the look at this question, okay, so which is equal to 0, so this you have to substitute, this is equal to 0. okay, so since in the question model number 1 is fixed is there, so you have to delete this. okay, so first column first row, here also first column first row. okay, so remaining what is left out, that you have to note down. okay, so remaining, okay, so after applying this, the node 1 is fixed, that is x1 is equal to 0, so after applying this deriving, so remaining you have to write down here. okay, so again you, so this simplify this equation. okay, so if you simplify this equation, okay, so this round as it is, again this you have to multiply this, you are going to get this equation. okay, so after simplification you are going to get the final lambda square lambda. okay, that is x square plus, this is ax square plus bx plus c formula. okay, so finally you are going to get this equation. If you simplify, multiply this, so you are going to get this equation. okay, so first as it is written, so multiply this, so you are going to get this 0.01179 lambda square minus 9158000 lambda plus 8 into 10 to the power of 14 equal to 0. okay, so this is form of what, a square plus bx plus c equal to 0. okay, so now if we solve by with the help of calculator, so you are going to get the lambda 1 and lambda 2 value. okay, so that is lambda 1 value is equal to what, 1.00300 into 10 to the power of 8 lambda 2. okay, so these are called as what, eigen values. okay, I hope you understand this, how to calculate the eigen value. Very simple. So k minus lambda m. okay, so you have to calculate the global stiffness matrix, elemental mass matrices, substitute, solve, you are going to get this eigen values, that is lambda 1 lambda 2. okay, so now our aim is to calculate the eigen vector. okay, so how to calculate the eigen vector now? So this is we know that, so natural frequency is equal to omega n square, which is equal to lambda. okay, so this is a formula you have to remember. So puts for the first element, so lambda 1, so omega n is equal to this, substitute that this value here. okay, so omega n is equal to 10015 radian per second. So this is what the natural frequency for the first one. okay, so this is what the angular frequency. So natural frequency is equal to this, we have the formula again, f1 is equal to omega n1 by 2 pi. So substitute this omega n1 we calculated here. So this is what the natural frequency for the first first natural frequency. okay, like that you have to calculate the again for the lambda 2 value similarly. So we have this again, so omega n2 is equal to 26008 is, so we have the natural frequency formula is equal to f is equal to omega by 2m 2p. okay, 2 pi. So substitute here n2 value, so here 2 pi, so you are going to get the natural frequency for the second element is equal to 4139. okay, so this is the natural frequency for the first element and this is for the second element. Now we have the to find the eigen vector. okay, k minus lambda m into x is equal to 0, but boundary condition x1 which is equal to 0. okay, so that is completely fixed is there. okay, so now this k value substitute already we calculated minus okay, so this k value wrote down here as it is. okay, already we calculated this. okay, value k minus lambda m value in the previous equation. okay, so here remaining is x2 and x3, that is node number 2 and node number 3 is there. okay, so this k already we calculated this. okay, so this value have to substitute. okay, so there. okay, here. Okay, so here x value is x1 is 0, so x2 x3, so x1 first row first column after deleting, so left out is x2 x3 which is equal to 0. Okay, so now you simplify this, so x2 x3 in terms of you are going to get, so x2 by x3 is equal to this. Okay, so but put lambda 1 value in the equation number 1. So for if you substitute for the lambda 1 value, so x2 by x3 is equal to 0.57. Put lambda 2 value, you are going to get x2 by x3 value. Okay, so these two are called as eigen vector. Okay, so this like this you have to calculate the eigen values and eigen vector. Okay, now finally to plot the mode shape, how to calculate the mode shape. Okay, to plot the mode shape, the normalization of the first mode is obtained by fixing the x3 is equal to 0. Okay, so x2 x3 is equal to, we calculated the x2 value, x2 0.57 okay by 1. Okay, so look at this, node number 3 is there. Okay, so this is initially fixed at node number 3, at node number 2, at node number this is x and y. Okay, at node number 1 is completely fixed. Okay, at node number 2 value we have, at node number 3 x3 is equal to 1. Okay, so this all are positive values there, just by approximation you have to put the, okay, and join this. So this is what the mode, first mode shape. Second mode shape is equal to what? So we got x2 by x3 is equal to 0 minus 0.57. Okay, x1 is at, this is a drop bar diagram, node number 1 2 3, at node number completely fixed 0, at node number 2 x2 nothing but minus is there, down positive down, up to negative down have to consider. So this is minus 0.57 and up 1 is 1 is there. Okay, so now you join this to this. Okay, so this is the second mode shape for the given stepped bar problem. Okay, so like this you have to calculate the eigen values and eigen vector for the given numerical problems. Okay, so here very simple, but you have to perfect well simplification. Okay, so I hope you understand this problem. Okay, thank you.